see. Magic if it works. That would be great. It's my first time using it, so don't laugh to me if I'm making mistakes. Okay.
Okay, so Hasti will talk about probing cosmic, historical, Lyman, A and history, Lyman, A emitters, and the Celtex experiment. So thank you very much. The stage is yours.
Thank you. Sorry, still struggling to understand. Okay, it works. Perfect. So first of all, thank you everybody for coming. Thanks, Simon, for giving us this opportunity to talk about our work here, and thanks to Shun for opening this beautiful window to work on. Okay, let's start by saying that I can do this first. Okay. Hydrogen is, as you know, hydrogen is the most abundant element in our universe. And this is a picture of Cecilia Payne. She was the first person discovering that. And actually, at the time, it was a very controversial result. She was discovering that the sun is mostly made out of hydrogen. But it was a very controversial and surprising result, so she was not able to publish that at the time. But now, the picture that hydrogen is the most abundant element in our universe is actually an established fact. So we know from the observations of cosmic particle background that only about 5% of the energy content of our universe is in the form of ordinary matter, like baryons, leptons, whatever we know from particle physics. And out of that 5%, 75% by mass is in the form of hydrogen, 24% is in the form of helium, and only about 1% are the other elements, right? So since we have this amount of hydrogen in the universe, so it makes total sense to study hydrogen light in emission and absorption. Okay, and I'm going to talk about basically the Lyman alpha in emission from the hydrogen. And it has been quite useful since this paper came out by Partridge and Peebles in 1967. So they are basically saying that if you have a distant star-forming galaxy, so there are some massive stars in that they are emitting photons, right? These photons are not going to escape the interstellar medium of the galaxy, but it's actually going to ionize the environment. It's actually going to create some H2 regions, and there are some hydrogen over there, and recombination will happen, and Lyman alpha photons will be emitted, right? And the point is that these guys were saying that if this is like a flux density in an arbitrary unit, so if this actually is from a distant galaxy, if this is equal to 1, the Lyman alpha emission will go up to 30. I'm sorry, I forgot that. Right? So yes, if this is 1, so Lyman alpha is like going to 30, right? So that's really amazing, because it seems that there are quite a lot of different types of energies with different frequencies are actually going to just show up in a single line. That is really, really useful for astronomy, right? And that's why we will start to look for Lyman alpha emission in distant galaxies. For example, here you can see one of the distant galaxies at average 8.7, which has been found by based on Lyman alpha emission. So let's talk a little bit about the HETEX cell. HETEX stands for Hobby Everly Dark Energy Experiment, and as pictured here, Shun is working on that. I mostly know. It's in McDonald Observatory in Texas, and the main goal of HETEX is actually understanding the nature of dark energy. And what they are doing, they are actually trying to increase the statistics of the measurements of Lyman alpha emitting galaxies to understand dark energy. And the story is that you are looking at distant galaxies, about 10 billion years ago, the photon. If any of these permitted transmission happens, Lyman alpha will be emitted, right? And it will hit your telescope. And if you zoom up, you see some optical fibers there. So your photon is going to hit these optical fibers, and then in the spectrograph of the telescope, they will measure how distant this galaxy is space. And that's the magic of physics. That this here you can see the stack of 50K Lyman alpha emitters, and you see how pronounced is this Lyman alpha emission. And just to show you where exactly Higgs is looking at, this is the beginning of our universe, right? This is the CMB. This is where we are, and this is how far, like redshift 2 to 3, basically 10 to 12 billion years ago. It's looking over there. Okay, now what we are doing, basically, we are trying to, in a realistic way, trying to model these Lyman alpha emitters. We are trying to understand how much Lyman alpha photons can escape from the interstellar medium of the galaxy and can reach to our telescope. So that's what we want to know, okay? So what we should do, there are some steps we have to do, okay? Okay, so the first thing we need is n-body simulation. It's not this. What n-body simulation does is that it tells us, it can predict the distribution of structures in our universe in larger scales. By larger scales, I mean gigapascal scales, right? And what we actually do here is that you know the distribution of, like you know the phase space information from of your particles. Basically, you are actually treating all the species of your universe as a single, only gravitating particle, in which you call it dark matter particle, which is collisionless. So basically, you are solving collisionless Boltzmann equations. On top of that, you have only gravity here between these particles, and you are basically solving Billas-Boltzmann equations, right? But this is not enough, because you need to know how these particles are gravitationally bound. And basically, there are different ways to find that. We call them dark matter halos, the gravitationally bound particles. There are different techniques to find them. One of them is called spherical overdensity technique, in which you find the local maxima of your overdensity, and then you have your collapse model. You can talk about collapse model. You find the Wheeler radius of the halos. In this case, your halos basically are spherical. There is another way, which is called friends of friend algorithm, in which you have you define a linking length, and you find the separation between your particles. And if those particles are the separation is smaller than the linking length, they are in the same group. They are in the same halos, right? And then you need to paint galaxy inside your halos, because that's the information we want to create a galaxy catalog, and that's a very like large field and very complex. There are many different ways to do so. There are different ways to put galaxies to inside dark matter halos. And by showing this picture, I just want to tell you that galaxies are residing inside these dark matter halos, right? And there are some halos over there, those blue ones that you see. And on top of that, I told you that we are interested to see how much Lyman alpha emission we can get from these galaxies. So what people do here is that, as you can see, they run Monte Carlo radiative transfer simulation, and that's the way to go. And here you can see, for example, the mean free path of Lyman alpha photon, which is actually doing random walk, you can see. I will go through these two last ones in a short time. At the end of the day, we need to calibrate our model. We need to use observations, and if we have some free parameters, we fix those parameters to the observation. So how is this galaxy halo connection works? There are many different ways. This is the way that we are using, which is an empirical model. So which is called universe machine model. It's a well-known model. There is a dark matter simulation, and then there is a connection between galaxies and halos in this in this way that you define a function for the star formation rate of your galaxies. Star formation rate means how fast in your galaxy the gas is going to be transformed to stars, right? The star formation rate of your galaxies depends on the mass of your dark matter halos that galaxy is residing in, and how these dark matter halos are evolving and how the masses are accreting depends to the star formation rate. And on top of that, you know, the full measure histories of your halos. And so you have a uniqueness, basically. You can find the stellar mass for your galaxies, and then you compare your universe with the real observations, and then your model of error, it has some parameters, and you do a CMC Monte Carlo Markov chain, and you fit those parameters using observations, okay? On top of this, we wanted to know how much Lyman alpha photons we would get. So to visually show that what are we talking about, these Lyman alpha photons are doing scattering, right? When Lyman alpha photons are scattering in real space, they are also diffusing in the frequency space. So as you can see this, if you have a medium like that, a uniform gas, and there is a Lyman alpha in the source in the middle, if it can scatter up to here, if the optical depth is like small, the spectra, the function of x is frequency here, will be like that. And if it can go larger, like further, if it can scatter and go further, it will be the distribution, like over the distribution of frequency will be broader, right? And people were solving this from 1970s, 1960s analytically, and also doing Monte Carlo radiative transfer. And this is what they would get. And there is a very good match on that. They get a double peak. This is a spectra of the photon trying to get out of this medium as a function of frequency, right? But this was for a static medium. In astrophysics, sometimes you have collapsing medium, sometimes you have expanding medium. So in this case, I don't know if you can see these green lines here. You have two peaks which have the same length, same heights, right? If you have collapsing medium, the photon, imagine the photon is trying to get out of this medium. The gas is starting to collapse, so the gas is warping on the photon, so photon gets more energy. That's why the blue side of the spectrum, which has a higher frequency, larger energy, it gets higher, and the other side will get lower. And if you have an expanding medium, exactly the opposite thing will happen. The red side of the spectrum will be higher. And that's basically the simplified model that we are using, which is called the T-shell model. We have a T-shell expanding. In this T-shell, we have neutral hydrogen, and in the middle of that, in the center, we have a source of Lyman alpha photon. Right? And this can go there, it can do scattering, can bounce back, goes to the other side, and then get out of the shell. So the shell also is expanding. It's a representative of an outflow. Okay, and we can parameterize the expansion velocity of the shell, the neutral hydrogen column density, and also the dust optical layer in terms of specifications of the galaxies, in terms of local astrophysical conditions. Can be star formation rate, million different. Okay, I don't want to go through that. And we have three parameters here. Alpha and beta. They are just three parameters of our model. Okay, and probably something easy. And if you change these parameters, you will see that your line profile as a function of wavelength is actually changing. If the expansion velocity changes, if the amount of neutral hydrogen changes, this profile will change. This is a work by Shun and his previous postdoc, that they were basically creating a package that it can do it very fast. Okay, that's not enough. So what we want to do is, what we want to know is that how much Lyman alpha photon reaches to my telescope, right? this is the spectra that I have from the interstellar medium, from the other side of the galaxy. But I know that the universe is expanding. This should go through the whole distribution of neutral hydrogen that exists in the wave until it reaches to my telescope. So since the universe is expanding, all the wavelengths are getting larger. So if I have a blue wavelength here, if it gets larger, it falls into the resonance. It falls into the resonance, and we will lose it. We will lose basically the blue side of our spectrum. And our red side of spectra will remain more or less the same. And that will be basically the transmission function. The blue side will be a little bit lower, and the red side will remain more or less the same. And here is how a line profile can change as a function of wavelength. So this solid line is what I get from the interstellar medium, and the dashed one is what I get from the IGN, basically. What I should have in my catalog and what I should compare with observations. And at the end, I should calibrate my model, right? What we get, the full information that we get from the galaxy surveys are basically two important things. The number density in each luminosity interval, the number density of galaxies in each luminosity interval, and the strength of the cluster in each separation interval. Okay, how clustering is strong in each separation, and then we basically use these two, and then we fit all alpha and beta parameters. We find the best fit, and then we have our catalog that can represent the real units. Okay? And the power of our catalog is that it's based on physical scenarios, as well as it can reproduce the real universe. Right? And thank you very much for this.
Do you have any questions for the audience?
Now, I'm a little bit lean for it. So my question may be too trivial. So galaxies and stars around galaxies have to form somehow. They have to form in a specific way. Now, one needs both dark matter and dark energy in order to explain the universe. Nobody knows really what dark matter is. It's gravitationally interacting and conceivably undergoes other very weak interactions. Certainly not electromagnetic interactions, otherwise one would have seen it literally. So my question would be, since your questions that you're investigating are also relevant to, star formation, do we need dark matter in order to explain the rate of galaxy formation that has been observed?
Yeah, of course, we have evidences for that. We actually have, please correct me if I'm wrong, we have basically some analysis that they compare the rotation curve of the galaxies. Then you include dark matter into your model, and then you don't include it. And what
that's the evidence for the existence.
That's the
yeah. But my question was: do we need dark matter not in order to explain the formation?
We know galaxies are residing in dark matter halos, and they are forming inside that. I think your question is very deep. I'm trying to find a way to answer. And we have evidences that dark matter exists from the CMB and from the rotation curve of the galaxies. For the formation of galaxies, we need dark matter. Well, I don't know the exact answer to your question.
Okay, but
I'm thinking about it.
We can discuss it. Yeah.
Thank you.
I probably missed this, but, you said like Lyman scattering, like you comes in like a very narrow range of regions, like a very small peak you see it. But then you said that you get a lot of spectral widening due to it scattering several or hundreds of times before it reaches your telescope. Wouldn't that cause the line to like no longer be observable as a single peak? So how do you tell what is Lyman scattering versus what is all the other frequencies?
Right.
Or like what's coming from things like that aren't from hydrogen that isn't in the halo.
Right. The shape of these spectra, it actually depends on the how fast your shell is expanding. If expansion velocity is very high, you will see much more differences between the two peaks. This is what is happening. The effect of the expansion. If neutral hydrogen is larger, you will see it's a little bit broadened, and there is the equivalent bit which actually increases the amplitude, and also we do have the bit itself. So all of these would affect the shape of the spectra basically. But you will, as you said, you will see it in a small range of wavelength, basically. Not very far from that, the line center, I would say. And the line center is 1215.7, if I'm not wrong.
But also, I think I missed earlier, why are there like the two different peaks on the?
Yeah, we have two different peaks. Actually, if you solve this analytically, or if you solve it by Monte Carlo, you will get two different peaks. Probably you can understand it in this way, that there is a positive direction to go and there is a negative direction to go for the frequency. That's why you will see two peaks here.
But those are like the negative frequencies on like a.
Yeah, in the previous slide, I was showing this spectra as a function of wavelength, but this one is as a function of frequencies.
Okay, so you're getting the green one and.
Yeah, here we are getting basically the expanding one. The red one is higher, and here the expansion velocity was very high. That's why you are not seeing the other peak at all, but you see the left side.
Okay, so and this is whether your halo is expanding or shrinking.
This is the gas expanding, the real material that we see.
Okay.
It's not the dogma halo. Like everything is happening inside the galaxy, right? Inside the interstellar medium of the galaxy.
Sometimes the actual volume of gases.
Yes, that's the real gas.
Okay. Okay, I understand.
Okay, great.